Yeah. Okay, so welcome everyone to today's seminars. I'm very pleased to introduce you to Cristian Barrera. Cristian is a junior faculty member at the Universidad de Valparaíso, in Chile. He received his Master in Science in Physics here at the Universidad de Chile under the supervision of Domenico Sapone, and completed his PhD at the Institute for Computational Cosmology at Durham University. Cristian is interested in cosmology, numerical relativity, and high-performance computing. And the title of his talk is Probing Relativistic Effects with Large-Scale Surveys. So please take it away.
Thank you very much for the nice introduction. Thank you for having me here today. So for today's seminar, I want to talk about a topic which is very close to my heart, which are GR effects in cosmology in general. So let me first start giving you some motivation. So the main idea is that because we'll have these very nice surveys in the upcoming decade. So for instance, we have Euclid, LSST here in Chile, and so on. So the idea is that because we'll have such precise measurements in the future, so these observations will be sensitive to effects that we may have overlooked in the past. So typically, to predict things, we simplify, we made some assumptions. So the idea is that, okay, maybe we need to kind of revise what we have predicted for observations and be kind of very careful and mindful about what we are dealing with. So this could be from the way that we model galaxies, for instance, to make the predictions. And there could be several effects that will come into play. So we have to kind of find out which ones are non-negligible anymore. And among all these possible effects that will come into play now, so I'm interested in these questions, namely, can GR, so some effects that we may have neglected in the past, coming from GR, so from the fact that gravity is not Newtonian in the end. So can some of these effects now be detectable? And if so, can we use these new effects to actually extract information from future surveys? So that's kind of the main idea of why it's interesting to look into these kinds of effects. So, what we mean by GR effects in a more concrete way. So people typically mean, they can mean two things. They are like two separate, in principle, concepts. They're not completely independent, though. So when people say, okay, let's look into GR effects. So one class is, oh, I'm hearing myself from somewhere here. It's a very, can we mute this maybe? Yeah, please. Okay. That's weird. Yeah. Okay, yeah, that's better. Thanks very much. Okay, yeah, so I don't get like in this loop. So some effects that could be introduced in observations are purely due to the fact that, as I was saying, gravity is not Newtonian. So in some aspects, we make predictions based on Newtonian gravity rather than in GR. And actually, when we do GR, we don't typically solve the full Einstein's equations, right? We do some approximations. For instance, we do perturbation theory, so we can kind of go order by order solving stuff, and we neglect some terms. So there's some truncation going on there. So can some of these neglected terms from Einstein's equation, for instance, introduce observable effects? So that's one type of GR effect, so connected again to the fact that we are doing GR rather than Newtonian gravity. And now there is this kind of second meaning to this term of GR effects, which is basically the fact that you kind of realize that when a survey looks into the sky, so you look at an angular position, or you point the telescope at a given direction, and you look into that direction, what is there? But actually in order for you to see a galaxy, what you actually have to receive is photons from that galaxy. And these photons, they have traveled across the whole universe, basically, so across an homogeneous universe, so they have been perturbed by the large-scale structure of the universe. So this actually will introduce some effects in your observations. So this is kind of the second meaning of GR effects. So of course, they are not independent. There's some overlap in between as well. But roughly speaking, there are these two concepts. So now let me start by, so we'll be dealing with both of them in this talk, but let me start with the second type of effects, so related to basically to light propagation. We'll come back to this first concept later. So when you consider then that if you're an observer and you have your telescope, you look into the sky, you see a galaxy such as in this image. So you have this, you point your telescope along a line of sight, you receive this image, but this is not completely true, right? Because the photons do not travel in straight lines in the universe, right? So what happens is that something closer to this picture, that so along a line of sight, what you see is not an object that is actually in that line of sight. The light is coming from elsewhere. So because this could be lensed, right, in your way to your telescope. So by all these intervening galaxies and gravitational potentials and so on. So this means that photons, so traveling from the galaxy to your telescope, they will be deflected and they could also be redshifted. So photons could also lose and gain energy in this travel. What does this mean? This means that when then you look at the full sky, let's say you have a map of the sky of all the large scale structure, and you kind of have your catalog as in this image here. You say, okay, I have this picture of the sky, what I see. Then let me define some pixels, some volume elements, and let me define the overdensity in this map. So that overdensity based on this image that you're seeing is not the true overdensity or the intrinsic overdensity in the universe. It's affected by all these kind of effects, such as lensing, for instance. So this is not a new thing, actually. So this kind of dates back to the late 80s. So Nick Kaiser pointed out this kind of fact that actually peculiar velocities themselves will impact the way that the distribution of galaxies that you observe in the universe. So this is what people call the redshift space distortions. So this is not, in this context of GR effects, is not a GR effect in this language, in the sense that it is well established these days. It's not a small effect either. So I'm not going to go into details here, but again, the same idea here is that if you imagine that you're looking, for instance, at a galaxy cluster, let's assume we have some spherical galaxy cluster. There's some matter infalling on large scales to form structures. And in the center, you have this kind of structure formation. So there's some realization going on there. You kind of have random motions in there. So you kind of have an inflow of matter on large scales. And then you have these random motions toward the center of the cluster. This is in real space. Then when you actually observe this thing, so you define this kind of line of sight in the vertical direction, what you actually see, because the photons, again, are affected by the kind of a Doppler effect going on because of the peculiar motions of the galaxies, what you observe is this kind of a squash distribution of matter. And this is what people call the redshift space distortion. So you have this squashing on large scales. So this is the Kaiser effect, or let's say the standard redshift space distortion. And on small scales, you have this elongation, which is due to, again, these random motions close to the center of the cluster. And this is what people call the fingers of God effect. So again, this is not a negligible effect, let's say. So it's a kind of order unity effect. So this has been already detected in data, for instance, in SDSS data. If you look at the data, you kind of see this distortion due to this motion of galaxies. So this is not the end of the story, though. So you can then try to generalize this argument by Kaiser. So basically what Kaiser said is that, so in the first equation, the overdensity that you observe, according to Nick Kaiser, along a given direction in the sky with a vector n, and at a given redshift. So this is related to the intrinsic overdensity of matter, which is the first term on the right-hand side. So this is in the sense that this overdensity is what you put in your energy momentum tensor, right? This comes from the theory. So what you observe is not directly this, but you have this correction due to the peculiar motions of the galaxies. So this second term, or actually the gradient, of kind of a gradient of this velocity field. So this will introduce this large-scale squashing I mentioned before. So again, you can kind of go all the way and generalize this analysis. So you can also say, okay, is this the only effect that comes into play when you try to map what you observe with the intrinsic distribution of matter? And the answer is no, there are more effects that come into play. And Bonvan and Dürer, they generalize this analysis, and basically doing perturbation theory at first order, you can show that actually what you observe in a map, let's say the sky, or density in the sky, is what Kaiser thought it was, but also you have some other effects, right? You have some contribution from weak lensing, so I'm not going into too many details here, but you have some extra contributions such as weak lensing contribution and then some other terms, and these other terms that scale basically like the Hubble horizon over moving separation in the sky. So these are what people call GR effects in this context. So there are still corrections to the observed matter over density field. So among these new terms, which are these GR effects in this language, so let me focus a bit on this gravitational redshift effect, which is kind of quite important in the community. So what is gravitational redshift? So this is the same that happens when a photon is emitted by the sun and arrives at the Earth. So in order to escape a potential well, a photon has to basically climb the potential well, and for doing so, it has to lose energy, basically. So this is what's shown in this sketch. So if you look at a potential well and you have these galaxies sitting there, so if they emit light and the light arrives at your telescope, so that light will be perturbed by this effect. So a changing in energy means a change in wavelength and a change in redshift, therefore. So kind of you start to introduce some perturbations to the redshift of photons because of these effects. So you have now, let's say, the background redshift of a galaxy, so determined by the cosmic expansion, but on top of that, these effects are introducing some corrections, small corrections to the redshift, for instance. So this is the effect of this, the impact of this gravitational redshift effect. Now, what is different from this effect? So let me show you a very particular property of this effect as compared to redshift space distortion that we just discussed. So this is squashing of the distribution of matter in the sky. So the picture I have here is the same we had before, but in a different way. So again, if we have an spherical cluster and we focus on two faint galaxies, this F1 and F2 here. So they are sitting like on the outskirts of this cluster. They are infalling. So you see then, because of this redshift distortion, you see this kind of squashing. So the apparent position is now like closer to the center. But then this effect, so the distance from each, so this effect, and maybe it's even clearer in this picture before. So the squashing here is symmetric. It's still symmetric with respect to the center of the cluster, right? So let's imagine we have a bright galaxy in that center of the cluster sitting there. So the effect still the same at the end. This is not true for the case of gravitational redshift, okay? So when you introduce this new perturbation to the redshift due to this effect, so the magnitude of the change of the redshift depends on where the galaxy is sitting in this potential well. So if you say, okay, let's focus on these two faint galaxies again, they are sitting at the same level of the potential well, so they are redshifted by the same amount. But unlike the previous case, so also the photons emitted by the bright galaxies sitting at in the deepest part of the potential, so you can also receive photon from that. And this is also redshifted, right? And it's actually redshifted by a larger amount because it's deeper in the potential well. What does this mean is that you end up with a picture like this, okay? So because the bright galaxy also is moving closer to you, apparently, now you have broken this, you have broken this as this symmetry that you had before. So now the apparent position of the bright galaxy, it's apparently closer to the faint galaxy that is closer to you than the one in the opposite direction. So this type of feature, so this type of broken symmetry in the distribution of matter in the sky is a particular property of GRFX, or some GRFX at least. And this could actually allow you to measure this effect, okay? Because it's kind of a smoking gun for this kind of effect. So people have realized this. So I'm not going to go into too many details here, but people realize that, okay, if you, this kind of pictures with one bright galaxy and two faint galaxies, this asymmetry that was introduced by this gravitational redshift effect, you can actually pick up this asymmetry if you, from a sample of galaxies, if you kind of take the full sample of galaxies and split the sample into bright galaxies and faint galaxy and take the cross correlation between these two populations of galaxies, this will statistically pick up this asymmetry, okay? People have done this in the past. So they have done some predictions for this, and you end up seeing something like this. This is kind of the shift in the distribution of matter. So you can see this is similar to the redshift distortion plot I showed you before. But now you see in this plot just kind of a shift along the line of sight. So it's not centered, right? And you also have some kind of small scale features there, which are again not symmetric along the line of sight. So again, this is a particular feature of this type of GRFX. And well, yeah, people have already proposed that we can use, we can try to extract this signal from future data and try to use this to prove basically the theory of gravity or lambda CDM. So just to wrap up this effect, so more recently, Bon and collaborators, they have also shown that this kind of effect and this asymmetry that this effect introduces could be also detected by DESI, having a very significant detection with DESI. Actually, they play around a little bit on how you define these two populations of galaxies, of bright and faint galaxies. Apparently, you have more bright galaxies and less faint galaxies. You kind of get a better signal for this effect. Kind of you reinforce this asymmetry in some way. Yeah.
These effects are very, very, very small scales, no? You can see that it's even lower.
Mm-hmm.
And
yeah, because
so everything is being done in perturbation theory.
Oh, it has been done from perturbation theory, but people have also done this based on basically Newtonian gravity in the way that you make your simulations nonlinear. So as Newtonian approximation, super-Horizon approximation, which is effectively nonlinear in that regard. This one?
Yes.
Right. Yes. Yeah, this is done with I think it's a simulation, some halos taken from simulations actually. So yeah, because so yes, you can try to predict this like statistically with perturbation theory, but for this kind of studies, because you have to basically have a mock galaxy catalog, so they typically build that with simulations. So, yeah, it is kind of a nonlinear prediction. Yes. Yeah, I don't recall in this case from Bon, but certainly the Croft prediction, the original prediction, let's say this one is based on simulation. Don't remember this new one, but yeah, probably. Yeah. Yeah, it's for DESI. Yeah, but in some sense, as long as you then yeah, it is non-linear. At the bottom line is it is non-linear. Yeah. Okay, so let me now kind of move back to the first type of effect I mentioned to you in this context of GRFX, which are maybe there are some effects that come into play because we are neglecting something in this, the description of gravity, let's say, okay? And this will lead us to this gravitomagnetism stuff, which I will try to introduce now. So we know that in full GR, so the space-time is twisted by rotating bodies, right? We know this for instance, from a Kerr black hole. So if you have a rotation and you put an observer, so the observer will be dragged around because of the rotation of the black hole. So in that sense, yeah, the space-time reacts to rotation of bodies. But this is not a property that is only valid for black holes. So this is a general property of the space-time, right? So you can actually try to measure this effect, not necessarily in black holes, but in other contexts. Of course, the effect will be stronger in black holes, but maybe you can try to look for this somewhere else. And people have actually measured this effect around the Earth, actually. So if you think, okay, there was this satellite back in 2011, so this called Gravity Probe B. So there was the satellite orbiting Earth like this, and because Earth is rotating, so it will start to slowly drag this satellite around and deviate from the original orbit. So as you may imagine, the effect is very small though. So actually from this figure, they say it's kind of a 10 to the minus 5 degrees per year effect. So we'll kind of slowly deviate from this original orbit. But the good thing is that the effect is cumulative. So people launched the satellite and they waited, I think, I don't know, like 2 years or something. I can't remember the exact number or the exact time, but they put the satellite out there, they waited enough, and they could kind of measure this effect, okay? So it's an effect that has been confirmed. It was not a very significant detection, I would say, though. I remember they had like large error bars, but at the end of the day, it was consistent with being non-zero, basically. And apparently, the effect exists as predicted by GR, okay? So now, so this is, again, the frame dragging effect. Now the question is, okay, can we measure this effect on other scales? Let's say, actually on cosmological scales. So far we haven't detected this effect, okay? But the question is now, can we detect this in the future? So this is what we want to answer now. So there's actually interest in understanding this effect on larger scales. Let's say there was this mission proposed a couple of years ago now by Tartaglia and collaborator to basically, again, do some space mission to measure this effect in the Milky Way now. So yeah, there is kind of interest to understand this a bit and to model this effect. Now, how can we model this effect in cosmology? Then again, we have to revise how we describe gravity. So it is not enough now to only deal with a scalar potential, this phi, okay, which is kind of what we deal with especially in structure formation in the late time universe. So we only care about the gravitational potential and that's it. So for this, we actually need to include some forgotten degrees of freedom in the metric, okay? So if you kind of do a weak field expansion of the metric, you can write down the most general metric like this. So you have basically two scalar degrees of freedom, phi and psi. You have this this BI vector field, which is kind of contributing to the non-diagonal part of the metric. So it's mixing space and time. And you also have this Hij term, which are extra perturbations here in the spatial part of the metric. So in the standard, let's say in the Poisson gauge, so the Hij here will be related to the two tensor modes of GR, so basically the gravitational waves, okay? And BI will actually contain two vector modes. So you have two scalars, phi and psi, you have two vectors in B, and you have these two tensors. So you have everything, every degree of freedom of the metric, basically, in this expression. So this effect that we are looking for related to frame dragging, as I said in this gauge, is appearing due to this vector field B, okay, this non-diagonal part of the metric. This is what people call the gravitomagnetic potential, gravitomagnetic field or frame dragging field. I will be using this term like the same, to mean the same thing, this term in the metric, okay? So this is very interesting because at some point especially when we study structure formation, we kind of only care, as I said, about the phi potential, right? And this is what clamps matter together, and this is what we need in principle. And we say, okay, even if there are some of these vector modes, for instance, generated in the early universe, they will decay over time. And we kind of say, okay, waiting long enough, we don't have them anymore, basically, let's say in a matter-dominated era, for instance. Now, this is true, but it is also true that, in some sense, this is true if you think about like first-order perturbation theory. But actually, if you go to higher order in perturbation theory, for instance, at second-order perturbation theory, you will realize that actually you could generate these vector modes in this B field dynamically by the products of first-order scalars perturbation. Basically, you have the perturbation of over density, you have the peculiar velocities, and the product of this, which is kind of a momentum field, this will actually couple together and source these vector modes dynamically. So they will be sustained by matter, basically, okay? By kind of rotational movements of matter, if you want. So it's fair to study them anyway. So this is kind of from a second-order perturbation theory description. They appear kind of a second-order in perturbation theory. Interestingly enough, you can also show that if you don't do perturbation theory, again, if you do kind of Newtonian gravity in a nonlinear way, if you do instead kind of a post-Newtonian expansion of the Einstein's equation, so you kind of go order by order, not in perturbations, but in powers of 1 over c, right? So you kind of get at the lowest order Newtonian gravity, but then you get as the first leading order correction in this post-Newtonian expansion, you kind of get this term, okay? So it's kind of also interesting to look into this at the nonlinear level, let's say. And actually, from this post-Newtonian expansion, you can then, in the same way that you can recover the Poisson equation in Newtonian gravity for the potential, which is sourced then by over densities. So doing this post-Newtonian expansion, you can actually write down and figure out the equation that this vector field satisfies. And it's something like this. So it's important in this equation, what I want to show you is that, so you have also kind of a Laplacian of this vector field. And on the right-hand side, you kind of have this 1 plus delta times V. So 1 plus delta is rho. So this is rho times V, which is the momentum field again. Okay, so again, this vector field is sourced by the momentum field. And the momentum field is just the product of density and velocity. So again, it's kind of a second order if you go back to perturbation theory, but this is kind of the nonlinear description of this effect, okay? So people have tried to, well, they have quantified kind of the, okay, how big is this, how large is this effect, especially compared to phi, okay? So one way is to compute the power spectrum of this new vector field. People have done that in the past based on second order perturbation theory, basically. So I will not go into details in this kind of expressions, but so you can compute the power spectrum of this vector field actually based on the power spectrum of the delta and velocity, basically. You kind of do a convolution, basically, and get this power spectrum, which is, again, a product of two things. So here I'm showing you on the right a plot for this. So we are looking here at the blue curve, okay? So this is the dimensionless power spectrum of this vector field. And as a reference, you can see the red line, which is the power spectrum. These are dimensionless power spectrum of the phi potential. So you see, okay, on very large scale, so very small k, so phi, it's kind of flat. And the power spectrum of this new potential, it kind of drops, right? So it kind of gets less and less. So if you take the ratio is very small on large scales, okay? Between blue and red. But interestingly enough, if you go to a smaller and a smaller scale. So actually below the equality scale or so on. So you can then this blue curve goes up. So actually the ratio in that region is not completely small, okay? So if you take the ratio between these two potentials, it's kind of almost 10 to the minus 4 or so. And then you say, okay, the potential are basically the power spectrum are basically the potentials square or the quantity square. So if you take the square root of that, this tells you that basically the ratio between the two potentials, the vector field in this gravitational potential, roughly speaking, is of order almost 10 to the minus 2. So it's almost like a percent effect. So it's kind of almost a percent effect. It's right below the percent level. So it is still interesting to try to understand this thing a little bit better, especially on smaller scales where the ratio is apparently larger, okay? So to look into this on a linear scale, so people have used simulations. So this is a bit tricky. I won't get into too many details here, but you may think, okay, if we want to use simulations, in simulations, you only have the gravitational potential, the gravitational potential phi, right? And you have matter and you have this potential, you solve the Poisson equation. But there's, in principle, this gravitomagnetic field is not part of the simulation. Right? You don't solve this in simulation. So because simulations only solve phi. However, because you know the equation that is satisfied by this potential under this kind of post-Newtonian approximation, you can actually use in some sense, use the power spectrum of the momentum fields as a proxy for the power spectrum of this gravitomagnetic field, okay? Precisely because you know it's satisfied. It's like relating the power spectrum of the density to the power spectrum of the gravitational potential. So there's some k-square factors and so on. So you can actually do the same and get some information and write down the power spectrum of this frame dragging field, okay? So people have done that. So actually, in principle, you don't need to run under this approximation like a full Newtonian, full GR simulation and so on. You can do it with Newtonian simulations and get this kind of indirectly, let's say. So people have done that in the past, and actually you can take out the ratio between these two potentials now on the small scales, okay, from the simulations. The ratio, though, I don't have a plot for the ratio, but interestingly enough, the ratio between the full nonlinear phi and the full nonlinear vector field and the full nonlinear phi, so this ratio is very close to the prediction from linear theory, to the ratio between the linear phi and the linear b, or second order b, and the linear phi, okay? It's kind of when you take the ratio between the two things, kind of you cancel out the nonlinearities in some senses. So yeah, you can actually predict this with perturbation theory at second order accurately enough, apparently. Okay, so let's now try to see, okay, what effect can this new vector field have on observations, okay? So that's kind of, we're going to now go back to this first discussion we had about photons and so on, okay? So one of the ways to try to understand this is, okay, again, figuring out the fact that this new vector field has on the propagation of photons, okay? You can actually think about computing and people have done that in the past, of computing the correction to the convergence field from the weak lensing, okay? So in the standard weak lensing, what you have is this kappa phi term. Okay, so kappa phi is the weak lensing convergence field, and it's basically given by this integral here in the middle. So this convergence field, if you look at a given direction in the sky with a vector n, so it's given basically by a line of sight projection of the matter along this line of sight. Okay, so you can look at a distant galaxy. If you project all the matter in between that galaxy and you kind of get this quantity, right? The convergence field. You have to weight this by some iteration lensing kernel. So you kind of have an expression for that. So this is what standard lensing do. But now the idea is that people have shown that because you have this new degree of freedom in the metric, you are taking this into account. So now you have kind of a GR convergence field, which is so you get this combination between kappa phi and this new term. You kind of get a correction to the standard with lensing convergence field. And this kappa b is given by the second equation here, which is roughly similar in structure, very similar in structure to the first one. The only difference is that you project not the matter or the over density along the line of sight, but you project actually the momentum field. So here Q is rho times velocity. So it's the momentum field along the line of sight, okay? So this is what determines this new contribution to the weak lensing field. Again, you have an integration kernel, lensing kernel, which is actually, yes, it's basically up to a constant. It's the same that you use for standard lensing, actually. So people have derived these equations in the mid-2000s or so. So, okay, so we have these equations. Can we then make some predictions for this convergence field? For instance, looking at the angular power spectrum of these quantities. So people have done this over the past decade or so. So for instance, on the left, so I'm showing you, so maybe you cannot see, well, yes, I think you do see the axis. So we're plotting the ratio between the angular power spectrum of these two components of the lensing convergence, so kappa phi and kappa b. So we plot the ratio in the same way that we're interested in the ratio between the two potentials before. And if you see this, oh, sorry. If you see this, if you plot this, make this plot, you will see the ratio between the two things is actually below the order of below 10 to the minus 5. So it's a very small correction to what we already predict from the standard weak lensing. Okay, so again, it seems a very small effect, probably undetectable. So this is for Euclid and SKA in the left plot. Kind of the same story is repeated later in this right plot, of, which is, okay, is again angular power spectrum for different things here. So it's a very busy plot, but let's focus on this green line, which is the angular power spectrum of kappa b. And then you have in black the power spectrum of kappa phi. Again, if you take the ratio, it is roughly the same as before. So it's a very kind of a sub% ratio of the angular power spectrum. And actually in this plot, you can see they put this magenta, well, this purple line. This is the noise level. I think this is for Euclid, probably, if I recall correctly. So actually the angular power spectrum of kappa b is below the noise level of the survey. So no chance to detect it, okay? Then people thought, okay, maybe we can try to look for a particular signature of this effect, okay? So unlike the scalar potential, so because this is a vector degree of freedom, so this will introduce actually B modes in weak lensing maps, okay? And you could say, okay, let's measure B modes in lensing maps and see if we can find something and detect something, and this will be related to this effect, okay? This is what Saga and others did. Okay, again, I'm showing you the angular power spectrum of the B modes induced by this vector field in this plot. So this is the purple line here, okay? And actually, again, you see this is well below the noise level of LSST in this case. So, so far, it seems that all these results are, well, they are all negative in the sense that this vector field will be undetectable by this kind of observations, at least, okay? So maybe you can, at this point, maybe you kind of start to forget about this and lose hope, okay? But let's try to not lose hope. So let's revise what we did before, okay? So all these results show you that, or they tell you that, okay, maybe this vector field B cannot be detected with autocorrelation, so auto power spectrum, okay? However, as I discussed before, for instance, when in the case of gravitational redshift, so that particular effect to measure it, basically what you do is to do some kind of cross correlation. So in that case, you kind of cross correlate two populations of galaxies, okay? So in that way, this allows you to extract this effect from the rest of things. So what about, okay, we try maybe to do something like a cross correlation in this context as well, okay? The question is, okay, let's say we are going to cross correlate the convergence field kappa GR with something else. Okay, what should be the something else to cross correlate with? Okay, fortunately enough, some also mid-2000 studies kind of passing by, they suggest that to detect this, to cross correlate with this effect of kappa B, you could actually use a particular effect, which is the kinematic Sunyaev-Seltovich effect. Okay, so this was already proposed but never done in some sense in the literature. Okay, so it was already there, the idea of cross correlation to detect this, or to try to detect this effect. Okay, so this is what we did, well, a couple of years ago now, based on simulations actually. So we quantified this cross correlation signal and see, okay, is it still this like very, very small, or do we have any chance to detect it basically? So first of all, a couple of words about kinematic Sunyaev-Seltovich effect. So if you're not familiar with it, so this is not related to galaxy survey necessarily. It's more related to CMB observations. It's actually a secondary anisotropy introduced on the CMB observations due to basically the intracluster medium. So because again, you have so many stuff, you have the whole history of the universe basically between you and the CMB or the last scattering surface. So in particular, you have galaxy clusters. So you have galaxies, but you also get like gas in between right there, forming structures and so on. So that gas has some free electrons there. So photons coming from the CMB, they can interact and be scattered actually by that intracluster medium, okay? That will introduce in turn temperature fluctuation in your CMB map. And this is what it's called the kinematic Sunyaev-Seltovich effect, so K as Z. So you can quantify this, okay, like in this equation below. So you can figure out this temperature fluctuations in a given direction in the sky. And okay, and you can quantify this related to the mean temperature of the CMB. You denote this, well, I denote this like this little b at least. So this, again, you can quantify this or calculate this, have an expression to calculate this, which is this kind of integral on the right-hand side, which again, if you look at it, is kind of similar to the integrals we had before. It's a kind of a line of sight projection from the observer all the way to the CMB in this case, in principle. And what you integrate, so interestingly enough, is again a projection of Q, which is the momentum field of matter, projected along the line of sight vector n, okay? So again, in this effect, also it's sourced by the momentum field in some sense, in the same way that this gravitomagnetic effect is sourced by momentum field, okay? So there's kind of an underlying connection already in there. So of course, in this case, you have some extra factors here, like optical depth, and so the cross-section for the scattering process between the photons and electrons and mean density of electrons and so on, okay? But in principle, the type of integral is sourced by the momentum field, okay?
Yeah.
Yes.
These are conventional the photons when they pass through the galaxy clustering, right?
Exactly, yes.
So the tau, the optical length, refers to the amount of gas given the cluster.
The optical depth, let me recall.
Is the, no, I mean, the photon scatters. No?
Yes, yes. Yeah, I can't remember the expression for the optical depth, but it's kind of, this CMB people, they know the expression, but yes, related to that, basically, to the, yeah. And actually, so you have to integrate this, as I was saying, up to the, actually, I think up to the end of reionization, which is redshift like 6 or something. So then you start to have like free electrons and so on. Yes, I don't recall the details for the tau, but in principle, yeah, it's related to that.
The left there.
Yes,
The CMD from
yeah.
adapting until
I think actually I don't remember. Actually, probably it's a function of the distance as well. I don't know if it's just a constant. It's actually, yeah, it's like a function along the of redshift, let's say. Okay, so we have some common ground here for these two effects, KZ and the gravitomagnetic effect. But this is not the only reason why this effect is so convenient to cross-correlate with, okay, as proposed by Schaffer and Bartelmann. So there is what I will call this a nice property, okay, of this effect. And what that allows you to actually cross-correlate, have a good cross-correlation, okay? The good property of the KZ effect is that it is not correlated with the standard kappa phi of the lensing, okay? At least at the 2-point level, okay? This is kind of a, people doing CMB and lensing, they kind of know this thing already. So this, okay, without going into much details here, but basically what this means is that, okay, kappa phi, you project density along the line of sight. For KZ, you project momentum, so density times velocity, okay? So if you look, if you explore the universe and if you, in one direction, you can see like an overdensity, let's say a cluster, like with a given velocity, maybe moving away from you, like this first blob here. If you explore the whole universe in principle, you have chances of encountering kind of the same overdensity or the same type of cluster moving towards you with the same velocity, basically because of a statistical isotropy of the velocity field, if you want. So this means that if you cross-correlate lens kappa phi and KZ at the 2-point level, and then you kind of average over the full sky, so this will be 0, basically. You will cancel out all these contributions because of moving towards you and away from you, basically, okay? This is kind of behind one of the reasons, or the reason why this is not, these two things are not correlated. Why is this important? Because, oh, I think I will try to speed up a bit. Why is this important? Because if you think about this, okay, kappa GR has its 2 components, which is presumably what you will get from observation, so everything together. Then when you cross-correlate this kind of full lensing map with KZ, so you will have these 2 terms in principle. So KZ correlated with kappa phi and KZ correlated with kappa B. And this property exactly guarantees that the first term is 0. So basically in this cross-correlation between these kind of 2 maps, what you pick up is just the second term, which if it is non-zero, that means it can be only non-zero because of this gravitomagnetic contribution in some sense, okay? So this is kind of will be like the signal that we'll try to quantify here, okay? And we'll measure precisely this frame dragging field. So this is why I call this nice property. So this is what we did. Actually, we used simulations to do this. Okay, actually Newtonian. Well, we use GR simulations, but we also use Newtonian simulations. So we said, okay, we are going to build this or construct these maps, sky maps, as I showed you before. How did we do this? Okay, you can. Okay, one way to do this is actually. Okay, let's say you have a simulation box, you have the large scale structure in the simulation, you put like an observer somewhere in the simulation, and you say, okay, I'm gonna shoot some photons from this observer in all directions, basically, up to a given distance or a given redshift. And in this process, you will basically say, okay, along all this possible line of sights, I will basically get the projected density. Okay, I will wait by the lensing kernel and I can construct then this convergence field, okay? So you basically do this kind of line of sight integral by actually moving through the simulation with an imaginary photon, let's say, and picking up the density field in every position along the line of sight. And you kind of do the same and record basically or project the momentum field along each possible direction. And you can construct then this kappa B term, okay? If you do this and you up to a given redshift, which is kind of the source redshift of your survey, then you end up having a sky map for this particular observer that you placed in the simulation box, okay? And this will contain, again, both contributions to the lensing. You can do the same, actually, again, to kind of build or to construct the CMB map for the KSZ, okay? Because again, what you do is to put an observer and do some line of sight projections according to this integral. So yes, you have to multiply by the correct factors there, but ultimately what you have to put here is the momentum field along the line of sight, right? So you, again, put the observer, shoot the rays, and record and project the momentum field of the simulation, and you kind of go, in this case, all the way to a very high redshift in principle, and you kind of have this temperature anisotropy map for the KSZ, okay? So you can construct both of these things, these maps from simulations. And then if you cross-correlate these two maps, so these maps will be literally some data in pixels, okay, that you have there, and you can cross-correlate this using some libraries, this kind of Hillpix libraries, and you can cross-correlate two maps and look for this signal, okay? Again, if you take this signal, in principle, this means you are picking up the physical signal you want due to this gravitomagnetic effect, okay? So this is what we tried. So this sounds very good in theory, but in practice, there are a lot of issues, and the ultimate issue we found in order to quantify at least the signal to noise from this approach is that when you shoot the photons, so from the observer, so if you think about shooting a photon, so you are the observer here and you shoot two photons, so in two very close directions. So these two photons, the separation between the two photons, basically they sample a very small separation in the sky, right? So it's like, if you look at the sky, but the sky is like right here. So you're looking at your hand, and this is a very short scale compared to other scales. And these are scales that are not resolved in the numerical simulation, okay? They are very small scales, so you have some resolution, spatial resolutions that basically kind of violate that or go beyond that because of this process, right? So, and this happens exactly because in the first shells, let's say, or the first photons picking up the contributions very close to the observer, okay? This will completely mess up the final kappa phi and final kappa b, and so on, okay? So this is kind of a numerical problem in this case, okay? You can learn a lot of things by doing this. You can quantify some other stuff, but for this purpose in particular, it will contaminate your signal, okay? I will not go into too many details, but it will render your signal to noise rubbish, basically. So what you can do instead, what we did instead was say, okay, to quantify the signal to noise of the signal, let's forget about the maps, okay? Let's forget about the maps. You can actually derive some expressions for the angular power spectrum of this kappa phi, kappa b, the KSZ, and so on, and also for the cross correlations, okay? If you do this Limber approximation, you can have these analytical expressions. And in these expressions, so they depend on the power spectrum, in the case of kappa phi, power spectrum of matter, or delta, okay? And in the other two effects, they depend on the momentum and the power spectrum of the momentum field, okay? In this approximation. So what you can do is to actually have this analytical integrals in principle under this Limber approximation, and then use to measure the power spectrum from the simulation, so they are completely nonlinear, and you kind of evaluate these integrals with those power spectrum, okay? So in principle, so you have to put some power spectrum there. You can measure this from the simulation and evaluate these integrals, okay? So this, we found this works, it's kind of better because in these integrals, you kind of have control, okay, over the scales you sample, because you sample scales which are L over, so a given multiple over the comoving distance. So you know when to stop measuring or sampling your power spectrum, basically. You can truncate that to 0 as opposed to the previous approach, okay? So that's very convenient. And this is what we did to measure all the signals. So, okay, I think I will try to wrap up very quickly because I don't have too much time. But okay, we computed the power spectra of this kappa phi and kappa b. Basically, this is the same as literature did before. We also computed the angular power spectrum of the CMB and the KSZ in particular. And also here, well, I put the noise levels of this different CMB experiments. And then I will not go into too many details here, but then you have to quantify somehow the signal to noise, okay? You want to get some signals to noise ratio. The signal, it is this cross correlation I just talked about. Now, the noise, it could be every source of possible contamination for your signal. So there are many things that you may take into account. So the bottom line is that, okay, you can, the most dangerous one, which is a potential cross correlation. Well, there's a cross correlation between the kappa phi and the ISW, the integrated Sachs-Wolf effect, which is imprinted in the CMB. These two things are correlated. The good thing is that they do not, they are very large on large scales, okay, as I show here, but they kind of drop towards the right, so toward the small angular separations in the sky, so they drop. Now, in this plot, okay, the contamination signal from ISW is this dashed line, so every color is a different redshift, okay, namely the redshift of the weak lensing survey, okay. And the solid line here is the physical signal that we want, KZ times the gravitomagnetic part of the convergence field. And in black, so different lines are the kind of combined noise of the CMB experiment and of the weak lensing survey, okay? So you see that actually, so this signal that you want is only above the noise levels, like on very small angular scales, like very high multiples, okay? But this is still like, at least for, okay, Planck, you cannot shoot up, the noise kind of shoots up. But for the future experiments, these are Simon's Observatory and CMB stage 4. So these are future CMB experiments. So noise levels are much smaller. So there's kind of this window here where you can actually try to detect this signal. Like it is above the noise levels, actually, not as previous studies, okay? So, okay, let me just wrap up with that. So we quantify the signal to noise in all these cases. So here I'm showing you, so every column here is a combination of a different weak lensing survey. So it could be LSST or Euclid combined with another CMB experiment. So where you pick up this KSZ signal. So Simon's Observatory or CMB stage 4. So on the top row, there's signal to noise. Bottom row is cumulative signal to noise up to a given L, okay? Yeah, so basically from this approach, you find that, yeah, actually signal to noise is, okay, for Planck, you don't get a signal to noise above 1, okay? But for future CMB experiments, because they are more precise, so the noise level is much, much lower, you kind of get a reasonable signal to noise ratio, okay? Like above 5 for a redshift of 1.4, okay, for the weak lensing survey. So in the cumulative signal to noise could be up to almost 10. So yeah, if you go to very small scales, you can actually try to detect this effect for the first time, basically. Okay, so let me finish with that. So just to summarize, so GR effects in general, they are very small, but they could kind of become new tools to extract information from future surveys, especially since they are very small, probably you need to have some kind of cross-correlation technique to detect them, okay? So they will not kind of completely contaminate all of your signals, but probably they will be relevant for cross-correlation studies, okay? People do cross-correlation for other purposes, and maybe you could also pick up kind of these signals that you forget about now, okay? So in the future, so kind of ideas that are interesting to look at based on this analysis, at least, is that, okay, maybe we can repeat this exercise in modified gravity, okay? So modified gravity, because you typically have a stronger gravitational field, you kind of get larger over densities, the momentum field is larger, so presumably these signals will be actually larger than in lambda CDM, so that would be interesting to look at and compare with future observations, okay? And another very important thing that we didn't do here, of course, because we use embodied simulations anyway, but since we are going into very small angular scales, so at this point you may want to include, and you definitely need to include, the effect of baryons, okay? You need to have some hydrodynamic simulations or some kind of effect of parameterization of effect of baryons, which will likely degrade this signal to noise, but yeah, you have to do this and quantify that, okay, to get a realistic signal for the future. So yeah, I'll stop here. Thanks very much.
Thank you, Cristian, for the very nice talk. Now, if anyone has any questions, maybe in the Zoom.
Step two, step two. So the first one is for the additional when you said, okay, when I shoot two photons, and of course I close it.
Yes.
I close it, and it's out of sense, no, there's not ready.
Yeah.
In this solution, you cannot resolve it. But in a way, it's a problem of because I was thinking, I mean, if you look very long term, the gravitational potential, the gravitational potential should affect all the photons, but in the long run, I would say.
Well, yes.
Yes.
Yes, yes.
And the question is, do you need this information in a way, or? Because I was thinking like that, backwards, you know, okay, you have photons coming and then.
Yes, okay.
Then they're affected by the local gravitational potential, which is a constant in a way, so we just take it out. It's, no?
Okay.
I don't know, just asking.
Yeah, that's no, it's a very good question. Okay, one of the things I remember I tried, I mean, I agree with you. In principle, you have to take into account, you cannot neglect this local information because it will affect your result, at least at some level, okay? At some, maybe it is a small correction in the end, I don't know, but you don't want to miss it. What I did try, I remember, was trying to say, okay, if we, so these maps, they are built like some kind of, with some kind of onion shell technique in some sense. You kind of stack different maps because you are doing line of sight projections anyway. So kind of store different maps and then you put them all together. I remember trying, for instance, okay, if the first few, so let's say the first 200 megaparsecs are problematic, let's skip these maps and just use the rest of information, like not projecting from the very observer, but from like a little bit beyond observer all the way to the target redshift. I think, yes, trying to do that, I mean, you can certainly do that and you will remove these numerical artifacts, but you kind of lose kind of signal actually from doing that. Yeah, so interesting. Yes, because since you are doing lensing, so you kind of get power from any scale anyway. So that's kind of the issue, I think. You could skip that, but this will lower your signal in the end. So this is why I think the second approach was, in that sense, better. Concise. Yes.
I was expecting this effect from the electromagnetic field to decay with the redshift. I mean, I thought that for a lower redshift the signal would be stronger, but in your plots, I think that was the other way around.
Let's see. So in kind of in this plot or later.
And I don't know why that happens. I want to ask.
Okay, yeah, that's a good question. It's not completely like trivial to see, but so the main. Right, so on all these plots, they kind of, the amplitude grows with redshift. And this mainly has to do with the kind of the same fact that we're discussing, in the sense that this is a kind of the target redshift of the survey. And if you go deeper into the sky, you kind of pick up more and more signal, basically. So the more that you go, the deeper or you go to the past, because all of this is kind of line of sight integrations. So you kind of get more and more signals. So this can only kind of grow with redshift in some sense.
I see. Yeah, I was expecting the other behavior because of learn that tensor modes decay with
Yes.
years, but yeah, that makes sense that the volume of survey surpass this expansion effect.
Exactly. If you look at if you don't do the integration, if you look at this vector mode like purely like directly, yeah, it will decay with redshift. But since you're doing integrations, you can only add up information anyway. So yeah. Thanks.
So I know there's also the thermal.
Correct. Yes.
Do you know if it's possible to be correlated with this kappa?
Yes, that's a good question. Yes. Yes. Actually, I think it could be correlated with the thermal. So you mean from the kappa with the thermal? Yes. It could be, to be honest, I'm not sure, but what I can guarantee is that, okay, to make this prediction, this forecast, we didn't take that effect into account, but for a particular reason, okay? And this is that people that work in CMB stuff, so here in this plot, I'm showing you basically different anisotropies contributing to the temperature map, basically. So you have lensing of the CMB, you can this KSZ, you have the thermal that you were mentioning, and actually you have some other stuff. But some of this stuff, so basically astronomers, they can do some post-processing and do some cleaning of the map. Okay, so precisely because this effect, the thermal one is frequency dependent. So this information, you if you exploit this information, you kind of subtract this effect from the map. So then only then you cross correlate. In principle, if you don't remove it, maybe it is correlated. I cannot guarantee, but yeah, it could be problematic if you cannot kind of remove these things. Yeah, it's also a very good question. Thanks.
What is it?
Yeah, this is the cosmic infrared background, so which is also contaminating the CMB.
Okay, if no further questions, let's thank Cristian again.
Thank you very much.